So just a minute ago, we talked about sampling from normal populations, so from normally distributed populations. And we're going to talk a minute about sampling from non-normal populations, which is likely to happen. A lot of populations aren't normally distributed. So we'll think about the sampling distribution of the mean as our sampling distribution. We're wondering, what about it when it's not normal? The population not normal, compute the mean anyway, do that lots of times, look at the kinds of values. What's going on there? It says the distribution won't be normal, but the mean is still the population mean. It doesn't help us a lot because we like to know the shape of the distribution, not just the center, but we have the center. The center is the old-fashioned center. And the standard deviation is the old-fashioned standard deviation. That's great. But in particular, we can't do probability calculations. In particular, Z and tables can't be used. So you need something fancier to compute probabilities for the mean if the population is not normally distributed. Okay. But luckily, look at this. There is a silver lining here. There's a fact called the central limit theorem that says if n is large, and for us maybe 30 is large, if the population isn't too crazily distributed, you can always make things bad enough that x bar won't be normal. But ordinarily, things you run into, if your sample size is at least 30, then x bar is approximately normally distributed. So averaging somehow produces the bell curve. The approximation improves as n increases. For slightly non-normal distributions, the average of even fewer observations makes a bell curve. So here we have a skewed distribution that we're sampling from, and then we're going to do an average of 10. And it looks like the skewness is basically gone. Nice. So this is almost bell-shaped. It's just a little bit skewed. Averaging gets rid of skewness. And so with even a small sample size, we'll take something that was skewed, as long as it's not too skewed, and turn the distribution of x bar into something that's not skewed. And if it was automatically almost bell-shaped, now it's going to look very bell-shaped, even with only averaging 10 values. So we'll look at that in a more sophisticated situation. We take a distribution of the scores on dice. So for them, a single die, you roll it millions of times, you ought to get about the same number of 1s, 2s, 3s, 4s, 5s, and 6s. Here's 1,000 rolls and their counts. They're about the same size, but there's a bit of variability there. We know if we collected more information, that would smooth out. But that's 1,000 rolls. And then we talk about rolling a die 10 times and computing the mean. So that was perfectly flat here. Now we're going to average 10 of those together. Now we saw when we just averaged 2 uniforms together that we will see. I can't remember where we are in this. So somewhere along the line we talk about density curves, and we talked about summing 2 uniform variables. That might be coming after this. No, we must have already done it. This is 8, right? Yeah, we're in chapter 8. We did that. Okay, so you've seen that triangular distribution that came out from the uniform distribution. So this is something like the uniform, except it's discrete. And we're averaging it 10 times, not just 2 values, but 10 values. And here comes this shape here, which truly looks like a bell curve. So even with something as not very bell-shaped at all, like rolling dice, an average of 10 gives you a pretty close to bell shape. And we said if you have 30, sort of no matter what you start with, you're going to get the bell curve out. And so if we were to do this more times, I imagine this would smooth out a lot, and we get a nice normal distribution here from just averaging 10 rolls of a die. Nice. So that's just examples of the central limit theorem in action. Averaging makes the bell curve. More values, more bell-shaped. And 10 is sometimes big enough, but 30 takes care of most situations. Okay. So it says that for a die, oh, we're going to do more work here. You can compute the mean for a die. We actually know how to do that. The mean is 3.5, and standard deviation is 1.707. And for the average of 10 rolls, the mean should be 3.5, and the standard deviation should be 0.54. And so we see that here. The 3.5 is showing up in the middle there. And if I go 0.54 over, it's about to here. So that kind of matches our thinking when I drew the bell curve on there, that the steepest point somewhere in here, and that's about the same place that we saw over here, 0.54. So everything's making sense here. The mean stays the same. The standard deviation gets divided by square root of n, even with averaging 10 rolls of a die. Okay. So let's do an example. Okay. Let's find the probability that in 30 rolls of a die, and we said 30 was enough. So it looked pretty bell-shaped anyway, but 30 makes it even more bell-shaped. Let's find the averages between 3.5 and 4.5. And we're doing 30 rolls. So that's the same as the sum being between 105 and 135. Sometimes when you compute those things, you would compute it using the sum. But we know the bell curve for, oh, I see. So there are two different things you might ask. You might say, if I roll a die 30 times and sum them, what's the chance I get between 105 and 135? And you can say, well, I compute that using averages between 3.5 and 4.5 and use the central limit theorem. But what that points out is you can use the central limit theorem not just for averages, but for sums. You just have to be able to compute the mean and standard deviation of the sum instead of the average. And the sum has to involve 30 terms from the distribution. But we'll just move on anyway. So we said the die has mean 3.5. Oh, the average between here and here. We're going to compute z values and see what happens. Okay, so we need z for 3.5, and we need z for 4.5. And then we'll find the areas and subtract. So we take the value minus the mean divided by the standard deviation. We got it here, 0.3117. And then we take 4.5 minus the mean over 0.3117, like that. Okay. And here we go. Well, the first one's just 0. Okay. So 4 parentheses comes up. 4.5 minus 3.5 divided by 0.3117. Parentheses turned it to a 9. Okay, parentheses 4.5 minus 3.5. I guess my hand must have been out of position and I wasn't looking at the screen. And we're going to divide that by 0.3117. Sometimes when you do homework and you're using your calculator and you get a number, you have no idea how you got it. There we go. Look at that. Minus 9,000. And what happened, I was hitting 0 instead of, my hand just slid over a little bit on the keyboard. Let's see what it really is. 3.208. Oh, that's pretty far. It's right though. 3.208. 3.208. That's 0. Okay. Now, I don't know if the tables go to 3.20. Oh, maybe they do. I thought that's pretty close to the end of the road. So, and the areas in the table here, areas, this is going to be 1/2 because it's in the middle. Which we could check it if you wanted to. Here's 0, it's 0.5. Okay, well, I write 0.5. We might want to subtract something. And here's 3.208. We'll make it 3.21 by rounding. We're in here 3.2. Come over here. 3.21 is 9993. And so the answer is approximately 0.9993 minus 0.5. 0.9993 minus 0.5. 4993. All right, so I think that gets rid of section 8.1, and then we'll head off to 8.2 as time allows. And there we go.